So thank you very much for this kind introduction. So first of all, I thank the organizers that I can be here. So it's always an honor and a pleasure to be back to India. I have stopped counted as many times I was in India already. So it's always a pleasure. And so you will see me here 3 times. So because they asked me for 3 talks. And they are organized as such that I will give two more, say, talks which are pedagogical, and then there is one which is, so to say, devoted to our recent research. So this is now one of the tutorials here, and I would like to talk about timescales. So you see also several names here. So these are PhD students and former PhD students I'm working with, and so they have also contributed, of course, to this work. Now, let me give you first a motivation. So why we are interested in that. And we are here at the workshop about climate. And so then one topic which concerns us all is climate change. And so therefore, timescales become now a focus in research, not only, say, in applications, but most of all also in mathematics. So why is this? When we think about environmental systems like the climate or so the climate compartments, ecosystems, whatever you think about, then the dynamics of these systems is working on a certain time scale. There is an internal time scale which organizes, so to say, the dynamics of the system. And this is one of the time scales. So we have to keep in mind. But when we think about climate change runs on another time scale. So because this is an external forcing, there are solar radiation, for instance, change in mean temperature or whatever you think is a measure of climate change. So this would also work on a time scale. But this could be different from your internal time scale of the system under investigation. So that has to be taken into account. And we have really to do this. And so not only when we look at the impact of climate change as a forcing on, for instance, ecosystems, but also if we would like to, for instance, and this is what we have seen here in many talks, couple different systems in a network, for instance, so that each node is, say, or represents a compartment of the climate system, then, of course, also in these couplings, so we have to take into account if we have different climate compartments, they work on different internal timescales, and when we couple them, these 2 different timescales are important in their interaction. And this is something I would like to talk about. And when we look into the literature, this aspect is often neglected. Often people think there is a quasi-stationary approach, which is valid, and that means, so we take our forcing, for instance, as given, but we assume implicitly that this is very slow. So this would be called the quasi-stationary approach. So you think that these changes are very, very slow compared to my internal time scale, and then you are back, so to say, to a treatment of your system as it would be a forced system, but with very, very slow forcing. And the slow forcing is practically, so to say, taken as almost stationary, so that it is just like a stationary parameter. And then you think about something like a bifurcation diagram for people who are familiar with nonlinear dynamics, which represents basically the dynamics of a system depending on a parameter. And then you think you are traversing this bifurcation diagram. So what I would like to do here in my lectures is I would like to convince you that if we really want to tackle climate change, this is only half of the truth. Because when these timescales are comparable, so the timescale of climate change of my driver, for instance, and the internal timescale of my, say, ecosystem or another compartment in the climate system, then something completely different can happen. And this is what we have to understand. And so therefore, I will do some methodology for this. And so when we look at climate change, we are interested in critical transitions. So we had already the several talks here where we think about critical transitions, so where we go qualitatively from one state to another one. And here are 4 examples, which I have just arbitrarily chosen, in a way, 2 from physics, 2 from ecology. And the transitions which we have here are transitions in so-called bistable systems. That means we have always 2 stable states which are coexisting for a given set of parameters. So Manish was talking about such things today. So this would be multistability, and this is even only bistability, which is a simpler form of multistability. So we have, for instance, in climate, the thermohaline ocean circulation. This is a large-scale circulation, which is very important for the climate in North and Western Europe. Why? So because it's a heat transfer basically from the tropics to the north. And you see, so the heat is transported to the north and released to the atmosphere here. And therefore, the ice cover, so this is the winter ice cover here, so is much more far north than in regions in Canada on the same latitude. So that means climate in Western and Northern Europe is on average 5 degrees warmer than in comparable locations in Canada. So this is a very important heat transfer. And this is a bistable system because it can be, so the heat can be transferred, or this kind of conveyor belt which transports the heat is off. So it can be shut down. It's known from paleoclimate that this can happen. So there's a bistable system. Part of it is a process which is called deep water formation. So here, this is a convection process. This happens where the heat is released to the atmosphere and then the water sinks down. And this is here. And this is a process which is also bistable. Either the convection is working or the convection is not working. It's another bistable system. And this is a time series here, which shows, so to say, that here in those years, this is end of the 60s, beginning of the 70s. So one of these convection chimneys, so these are located areas, so in small locations in the ocean, so was shut down. And this weakens the whole transport of heat. So this is also a transition which can happen. Or we have here also in data the change in dominance of different species in the North Sea. Or what is depicted here is a change also from one state to another, which can happen in shallow lakes and changes the whole biodiversity in this case. So we have lots of species in this case, and here the whole lake is dominated by plankton, by phytoplankton, and all the plants which are here on the bottom, so they die out. And again, it's a bistable system. So now when we think about this, so I would like to remind you, so what multistability is, even though Manish has already described it in the morning. So we have basically several stable states. Here it's also only shown as a bistable system. We can think about it as a kind of potential landscape. And we have 2 stable states here, the blue balls. So these are the attractors. And then we have a red one here on the top. And so this sits on the basin boundary. So already Manish told you that there is a basin of attraction associated to each of these attracting states here, these stable states. And this is the set of initial conditions which all go to the same stable state, which is here. Now, the coexistence of stable states is a typical property of nonlinear systems. And when we think about the climate system of ecosystems, there's all highly nonlinear. So that means this is a typical property we have to expect when we talk about climate or when we talk about ecosystems or other environmental problems. And basins of attraction are crucial because which of those different stable states is realized depends really on the initial condition. Because you can think of this as a landscape and you are just throwing a ball and you look how it rolls in this landscape. So then, so you would see so that it depends crucially where you put the ball in the very beginning, where it rolls, and which of these stable states you are going to reach. Now, no, it was too fast. Okay, so these are the typical tipping mechanisms which are known so far. I will not talk about all of them. So two of them I will mention only, and two of them will appear here in this timescale talk. So there are more than that already. So this is not the state of the art. There is another one, p-tipping, so which has been discovered recently. But what a bifurcation is, hopefully many of you in the audience will know that. This is a qualitative change in the dynamics of a system when you change a system parameter. So you can compute it in a model system. And this is one of the simplest bifurcations here. It's a limit point or a saddle node bifurcation. And that means you have a parameter here, you have a system state here. And then, so this would be the long-term state. This could be stationary, could be periodic or whatever. And then you go to this cliff here, basically, slowly, and then you jump over, and then this would be a bifurcation. So this would be called a bifurcation tipping. So because this is a qualitative change and you cross a threshold here. Another classical one is a noise-induced transition, so where you have also a bistable system, but you are jumping between the two different wells due to the noise. This would be a noise tipping. Then there would be another one possible, so which is called a shock tipping or an extreme event tipping. So where you just go with one perturbation, one large perturbation, you are jumping over this state here. So in the noise-induced tipping, the noise would not act here, so it would act here, but it would bring you, so to say, over this maximum, which we have seen in the stability landscape. So, but a noisy trajectory would take quite a long time to reach this point and then jump over. In a shock tipping, you would go to another basin of attraction just at once. So there's a large perturbation and it kicks you into another basin of attraction. And finally, so to say, rate-induced tipping. So this is what I will mostly talk about today. This is a kind of tipping which happens in non-autonomous systems. And this is what's the focus of all my talks. Because what's happening is when your time scale of climate change is very slow, so you are changing this with a trend, then you would end up with bifurcation tipping if there are critical transitions in this system, but your parameter is changing very, very slowly. So then you are crawling around here along this branch of stable solutions up to the bifurcation point, and then you jump. But in a rate-induced tipping, so the rate is comparable to the internal time scale of the system under investigation. So that means you cannot make this kind of quasi-stationary approach. You have to go along this, so with this rate, and that means you have a non-autonomous system and with an arbitrary time dependence. So we know in nonlinear dynamics, we know periodically forced systems, so there is a well-developed theory. So for all attractors, bifurcations, and whatever, for rate dependent processes, this is not available. So we have to work on that. And rate tipping is one of them. This is a bifurcation in a non-autonomous system where not the value of the bifurcation parameter, so to say, is the threshold, but the threshold is a critical rate. So the system cannot track its original state anymore. But when the forcing is too fast, it cannot track, it loses track and tips. And so this is a truly non-autonomous dynamics. Now, so therefore we look at this, and our challenge here is to really look at the timescales which play a big role. And so this is the main issue which I would like to talk about. I would like to mention only so that there is this dichotomy here between resilience and regime shifts or instabilities and tipping points, three different words for the same thing, basically, but it has been developed in three different disciplines. Regime shift is mainly used in ecosystem dynamics. Instability is more in mathematics, tipping point in climate science. And there is, so to say, a counterpart, which has been originally developed in ecology, so by Holling, who talked about resilience and defined resilience as the return to its original state after a perturbation. And so these two are closely related. And so therefore, all these tipping or critical transitions are related with this concept as well, because if you have a tipping, then your system is not resilient and vice versa. Well, wait. So what are tipping elements in the climate system? So this is already an old figure, as you see. This is from 2008. So what is shown here is in the climate system, the different tipping elements. So what are the critical elements in the climate system which could change when we talk about climate change? And we see quite a bit. So in red, we see all the circulation patterns. So we had already talks about the Indian monsoon, El Nino was mentioned. But there are many others here as well. So then we have the ice sheets. So Arctic, Antarctic, or the Greenland ice sheet. And then we have the vegetation patterns, basically the boreal forests, the Amazon rainforest, or the tropical coral reefs. All are threatened by climate change. And we have to understand this. And I would like to focus here also again on the timescales. So when we look at all those, probably I have to stand here. So this is also a table from Lenton's paper, so where we have on the left side all the different tipping elements, but I would like to focus here only on one column, and these are the transition timescales. And then you see Arctic summer sea ice, which is under discussion, has a rapid change, could be only 10 years, which takes it. But when we think about the Greenland ice sheet, then it's already more than 300 years. The Atlantic thermohaline ocean circulation, so this Atlantic heat transfer to the north, it's about 100 years, and maybe this is not even true according to latest papers. It could be much faster, and so on. So we see that lots of different timescales are involved here, and we have to deal with this. We have to deal with very different timescales when we talk about the impact of climate change on certain elements of the climate system, and this is something so we always have to keep in mind, and we have to develop mathematics how to deal with coupling these different timescales, because we have to solve it also mathematically. Now, this becomes particularly important when you start coupling these climate elements. So this is, for instance, one possible tipping cascade which one can think of. So the Greenland ice sheet is melting, then this could cause a tipping of the Atlantic overturning circulation, because freshwater input is one of the main parameters, and this would change dramatically if the Greenland ice sheet melts. And then we would have another critical transition here, that the rainforest dies out, because if the thermohaline ocean circulation changes, then we could here imagine that there will be a drought and not so much moisture is getting to the Amazon forest. So these are tipping cascades which are studied nowadays. And that means we are coupling now systems with very different timescales. Again, so to say, a problem which we have to tackle. And the same happens in ecosystems. So because these two will be today, so to say, my topic. And in ecosystems, so you have food webs, or in a simplified version, you have food chains. And so when you think about such an ecosystem, then timescale separation is something which is always present, because there is a thing which is called allometric slowing down, and that means the timescales of the different levels here, trophic levels, are different. So the higher you go in your trophic level, the slower becomes the turnover time. That means the lifetime of the species. So if the plankton, for instance, phytoplankton has a doubling time of 1 day, zooplankton already of several weeks. When we come to fishes, then we are already on a time scale of years. And so this goes up the whole food web. So that means we have here a timescale separation always when we talk about ecosystems. So that means you would have, if you model those things, you would have a species n on the nth trophic level. So then it would be in a food chain, for instance, be determined by gains and losses. But you would have a factor here in front of the whole thing, so which determines the timescale separation between the different species. And this is all what we have to take into account. How do we do that? And now we come to the methodology. So how can we deal with this? Let's do it with an ecosystem model. So we have a predator and a prey. And we have two equations. So one is for the prey, one is for the predator. So you see these symbols here. And the timescale separation is hidden in this parameter. So there is a parameter which basically separates the two timescales for the prey, which is the fast variable, and the predator, which is the slow variable. So now when you look at the dynamics, for instance, in state space, so you see that the dynamics also reflects fast pieces of the dynamics and slow. So you have a slow part here. So this is a limit cycle, then a fast part here, a slow part here, a fast part here. Now, so to tackle this, we can think about singular perturbation theory. And that means, so to say, we consider the limits also where this timescale separation goes to zero. So that means, so we can do this, we can consider the whole thing in two different timescales, in a fast timescale and in a slow timescale. And the dynamics would be completely different. But then we can understand what's going on in this system. And this is the big advantage of the whole thing. And let's do that. So first, we go into the fast time tau. And that means our phytoplankton, for instance, so the fast variable is fast. And so we are having this dynamics here. But so the predators, this would be the prey. So, and the prey develops fast. The predator, in this time, when we look at the dynamics of the fast variable, changes almost not. So therefore, this is zero. So we are going to another time scale. So because what I showed previously was the slow time scale. So now we are in the fast time scale. And then this doesn't change. So what we get is a layered system. So V is basically constant. So because it doesn't change in time. And then, so we have these layers and we look at the dynamics. So this is our dynamical system and we look what it is. And then we see, so to say, the green stuff here are the trajectories which are moving fast and they are moving in different directions. So you see, so this, if you start here, you go here. If you start here, you go here. So this would be the dynamics in the fast layer system, but you can also look at the slow reduced system. So now, it's different. So you see now the fast dynamics is zero. And now the slow dynamics is what matters. So what does this mean? So that means we are assuming that the fast one, the fast variable, is almost instantaneously going to this function, so which is an algebraic condition. And then we look only at the dynamics on this function. And this function is called the critical manifold. The critical manifold is nothing else than the null line here. And we can plot it here. So this is the green stuff. So this would be this null line. And the slow dynamics happens exactly on this green curve. So this is the slow dynamics as we have seen. And now this critical manifold can have stable and unstable branches. Why? When we go back to our fast layout system, so then we see, so the fast dynamics goes here. That means the slow dynamics, so this critical manifold, is a collection of stable points or unstable points in the fast time. So that means we have stationary points here in terms of the fast system, and they can be stable or unstable. And this brings us to a very nice concept, because now we can look at this in terms of a critical manifold. Now we have stable and unstable parts of the critical manifold. And so we have the blue ones are unstable, the red ones are stable, and now we see what our dynamics is doing. So it's moving slowly right here. Then it comes here, it's jumping over to the other stable part of the critical manifold. It's going down here again slowly, and then it jumps over here again, so to say, when this becomes unstable, so then any kick is sufficient to kick it again here, and that means this is finally the overall dynamics which we are going to see. That means the trajectories are attracted to the stable critical manifold, and it's repelled from the unstable ones. This will help us, so to say, to explain the dynamics. Now, when we think about it, so then these critical manifolds, we have computed under one condition. Because what we have assumed is that our kappa is 0. Our timescale separation is 0. It's extremely fast. So the timescale separation is practically infinity. So between the two timescales. Now, this is in reality, of course, not the case. Okay, so this is an approximation. So what we have looked at was this critical manifold. This is this thing. In reality, when the timescale separation is not exactly, so to say, infinite timescale separation, then these two parts, the stable and the unstable parts, are distorted. And they are not matching so nicely as we have seen this before. So because this is a limit case, which helps us to understand the dynamics, but in reality, we would have something different. So we would have different parts of this critical manifold, so which would work here in this system. Now, let me. So I think there are some. No, it's fine. No. Okay, so now let's look at this. What is happening in this case? So because we have seen that there is in the critical manifold, there is one critical point. And this is this fold point here. So now we see in terms, so to say, of the dynamics on the critical manifold, so or in the fast layout system, we see this is a bifurcation point because there is a stable solution and there is an unstable solution. They merge and we have something like a saddle node bifurcation. This is here. So what happens in the whole dynamics when the system comes here, basically, to this fold point, and now we look again to the infinite limit of timescale separation. So here the velocity of the trajectory becomes infinitely large. So why? So we are having this dynamics. We are looking at the slow dynamics on the critical manifold, but we are approaching, so to say, this point. And doing so what we compute then is we make a transformation such that we project the fast dynamics onto this critical manifold and look what's happening when we are approaching this point. And then this would be now the fast dynamics on the critical manifold. And then there is something here in the denominator, and so this determines, so to say, the dynamics on this critical manifold. But this function here is the derivative with respect to u, and here this is just 0, this derivative. And that means, so this is in the denominator, so we see the speed of our prey becomes infinite, and it just shoots off and goes to this critical manifold here. So this is the role of this fold point on this critical manifold. But there is one particular trajectory. One particular trajectory in the system where what is, I forgot to change it, I just see that I forgot to change the, so the variables here because I put it on the other slide with other letters to make it, so to say, equal for the whole talk. Okay, sorry. So, but this this function here in the denominator can also be 0. And this is a very particular situation. Then we have here something 0 divided by 0. And this is the only trajectory which goes practically over this fold point without having the speed of this fast variable going to infinity. So it really goes, and this solution is called a Canard solution. The Canard solution is also very important. So as we will see when we look at this in an application, so what it is good for. So now I think we have all the ingredients theoretically. So what is behind what we are going to see now in an application? Now let's have a look at the Rosenzweig-MacArthur model. And so this Rosenzweig-MacArthur model is, I would say, the paradigm in theoretical ecology. So this is the most studied model ever, I would say. In theoretical ecology, it's just a predator-prey system. So you have a logistic growth here for the prey, then there is a predation. So the predator grows and it dies. And then there is a timescale separation because the prey is much faster in its development than the predator. So it has everything what we want to have to really look at the dynamics of this system. Let's have a look at this dynamics. And it's controlled by the carrying capacity. Maybe I should go once again back. The carrying capacity is one parameter here, which is the environment. It encapsulates the environment for the prey, so to say, what is their food, basically. And then we look at this, and we go now and change this carrying capacity. Let's do it first in a bifurcation way. So to see what type of bifurcations we have in this model, because there are two, there is a transcritical bifurcation, so where the predator can invade. So because there is an interval where only the prey survives and the predator dies out. Then there is a stable coexistence of predator and prey. And then there is the limit cycle we have seen already. So when the carrying capacity becomes large, so then predator and prey can oscillate. And so now we would like to go on rate-induced transitions, and therefore, so we exclude bifurcation transitions. So we use now, so to say, an approach to change this carrying capacity, but avoid these type of bifurcations. So we are changing our carrying capacity far away from the bifurcations so that we concentrate only on this case where predator and prey are coexisting. So let's do this. And as I said, in rate-induced transitions, we have this interplay between the two different timescales. So we would like to show now the machinery which we have learned how to tackle a real problem with this machinery. So we have a non-autonomous dynamics. And then, so to say, we have the two timescales. So we have the rate of the external parameter. So we are changing our carrying capacity with a certain trend, which is also, so to say, comparable in its rate with the internal dynamics. And we have, of course, the internal dynamics. So we can think of many things, so what we can change in an ecosystem. So we will choose the first one, we change the nutrient conditions. And there can be two types of critical transitions. One would be a tipping to another state in multi-stable systems. So we keep this out. We will discuss it tomorrow in another talk. But we want to focus here on a rate-induced transition where we have only one state, no alternative state. So it's just one stable state in this system, nothing what is alternative. And we would like to show that there is also a critical transition. So this is the same model as you see, but now we have an additional equation. So this is the habitat quality, and this is changing K, and we decline it. So we make the conditions worse. We do it all the time with land use change. Climate change is usually deteriorating our conditions for the prey evolution. So that means we do this here over some time. And as I said, we want to avoid bifurcation tipping. So therefore, we do it only in an interval, so where we don't touch any bifurcation, so that we have just one stable state. And this is what comes out. So we see now two situations. Now we have a three-dimensional state space. It's predator, prey, and capacity, because capacity is now another state variable, even though it runs on a different time scale, but still it's a state variable. Now we have a three-dimensional space. Again, so I show here the critical manifold with the same color coding as before. So we have here the stable branches in red, the unstable branches in blue. This is one rate. And here the prey tracks its original stable state. Tracking means it stays in its neighborhood. And here, when the rate is too large, so too large means that so there is not much of a change, as you see. And we start with the same initial condition here, and then the system will tip, because it goes over this fold here and reaches an area, so of the reaches, so to say, the neighborhood of this critical manifold, where the prey concentration is so low that you can, in a real setting, the prey would be extinct. In a mathematical setting, it does not, so it goes back because it cannot reach this manifold. This would be exactly zero when it would reach, but dynamically this cannot be. But we see beyond the critical rate, the system collapses. So the prey gets extinct, and finally also the predator, so the whole ecosystem would collapse. Come on. And here we can also illustrate now what is the role of this canard. So because we already saw that this canard trajectory plays a very important role, and there is this fold point here on, so to say, there is also a singular point here on this fold of the critical manifold. And this is exactly the condition where we have this one trajectory which goes over the fold. If we are here, so then my trajectory would, for kappa non-zero, so this is the zero case, would jump off. And while here, it is repelled from the fold and it's tracking. That means this canard has a very particular meaning. It is like a basin boundary in a way. So it's not a basin boundary, what we know from dynamical system theory. So it's not separating two different stable states in that sense, but it separates tracking and tipping. And that means you have initial conditions which tip, which are all here. And you have initial conditions which track, and they are all here. And that means when we come back to our example, so we see our canard trajectory here, this would be initial conditions which tip, and these are the initial conditions which track. So that means we know now tipping depends on the initial condition. And it's so this is a general phenomenon. So this tipping often depends on the initial condition. So when you tip or when you track. Wait. So, okay, so this was basically what I wanted to say on the rate-induced transitions, so how you can tackle them, and what are the timescales and what you can do. So what is the methodology to do this? Now I would like to bring another example as so to say that we see also that timescales are important for other tipping phenomena. I would like to have a look at the noise-induced tipping. Noise-induced tipping is known for, I would say, 50 years. So first it was studied as noise-induced phase transitions, and then later as noise-induced hopping between different states. So this is just a trajectory in a multi-stable system. When you put noise, then it can jump between the different states, and we see that it jumps here between the two stable states here, and under the influence of something which is just fluctuation. So this is just noise. Okay, so then an example I have already mentioned is this deep water convection, so which happens in the Labrador Sea and also in the north of Iceland. And so then you have, so to say, a very localized process, so where convection takes place, and it can also have two stable states. Either you have yearly convection, it's usually in February, or you have no convection, that means no deep water formation, and then it would weaken overall the Atlantic overturning circulation. Now, when you put noise on the system and then you look at a model system, so which is parameterized with the data I showed in the beginning, so then you see your potential landscape upside down. So this is now a noise representation of your stability landscape. It's not exactly the same, of course, but then you see, so to say, for the data we have for such a non-convection event, so we see that non-convective years are much more frequent than convective years. And you need, for this type of transitions, you need another measure, another stability measure, which is the mean escape time from the potential well. So this you can also study in climate change, and it would mean for this convection process that with increasing global warming, this mean escape time, so to say, would for the non-convective times, so to say, or years, so it would be that the non-convective years, you stay much longer. You can immediately imagine, because what is here in the nominator is the potential height you have to overcome, which is much larger here. And and these would be the convective years, and then so to say, so there you jump off very quickly. So global warming would kick us out much faster from here and not from here, which would mean a weakening of the overturning circulation. Now, so we have not talked about timescales yet. So because you can study this in any bistable system now, this kind of hopping process. And what is important is also, how do you go from one stable state to the other? So when we think about it, then, so to say, the usual case is, and this is known for decades, that you go over the saddle point. That means this maximum which we have seen in the potential landscape. So this would be, so to say, the basin boundary here, the yellow thing. So then you have the two stable states here. And then, so to say, you go with the most probable exit path, you go over the saddle point and reach the other state. This would be an example for this, where we have a timescale separation in principle, which for those figures is not there. So there epsilon is 1. And so this would be the Fitzhugh-Nagumo model in neuroscience, which has also a nice timescale separation. And so this is a model we probably all know. Most of you will know this situation where we have excitability. But when you shift this line to here, then you have bistability. And this is the situation we are considering here. And then this is, so to say, a color coding of the quasi-potential. So because you can compute this potential landscape also for higher dimensional systems, this is the color coding. So that means we have a deep well here from which we go over the saddle point and come here. And this would be the landscape, cut through this landscape along the basin boundary. And then the saddle point is the minimum. This is where you go over. This would be the saddle point over which you basically go in this landscape. It has, so the name saddle point is like, because it looks like a saddle, so you have, so to say, so to two sides, it goes like this, and to the other side, it goes like this in a two-dimensional system. So now let's take epsilon into account and look at this. So we have seen this now, but we go now to a timescale separation here. So this is an increased timescale separation. This is basically a timescale. This is no timescale separation. It makes it even stronger. So, but we look to the left. And now we see again, so to say, our process. And now we see the most probable exit path, if we would compute it, so to say, with a tool, so which is also using these quasi-potentials, we would go over the settle point. But this is not what the trajectories are going to do. So the trajectories do the blue paths here. So the blue paths are not as here on top of this one, so that we have a distribution of trajectories on this, but it goes over on another place. So we are jumping through the boundary on another place. We are not doing this on via the settle point. And the more we focus, so to say, on timescale separation, the more we just shift on another point in the state space where, so to say, we go from one basin of attraction to another one. So we are not meeting this condition anymore. And the secret behind it is when we look at the quasi-potential, so here it's not very nicely visible, so but you see, so this is all the same color. That means the quasi-potential has more or less the same value. If we now make a cross-section around the boundary and look at this, then you see that there is this plateau. And that means the trajectory can go over anywhere in this plateau in principle. But it chooses, of course, so to say, the slight minimum which pops up here. So again, timescale separation changes critical transitions, also the classical ones, which has been completely overlooked over all these years, because so noise-induced transitions are known for 50 years. So timescale separation has never been an issue, so which was considered. But for climate change, we need to do this because particularly for the thermohaline ocean circulation, timescale separation is huge. And this brings me to the end. And which I would like to bring across here is timescale separation is when we think about the climate system, and we want to study climate change, we have to take this into account. This is a must. So because you always have to see what are the timescales of the different systems you are maybe coupling. You are maybe looking at timescales between forcing and internal dynamics. Timescales can change all the type of critical transitions. So this is something which you have to take into account. And in ecosystems, you have always a timescale separation. There's no way around it. In the climate system, so you have it always when you try to couple two different, say, tipping elements, you end up for sure with timescale separation as well. And mostly also when you look at climate change as the driver of critical transitions. And critical manifolds is one of the useful tools which you can use to analyze slow, fast systems, which you often find in climate dynamics. So this is a very useful tool. It's not so difficult as it might have looked like when you see it for the first time. So it's relatively easy, so to say, to apply. And the gain you have from using these type of tools is enormous, because it helps you understanding the critical transitions which happen in these kind of systems. Another tool is snapshot attractors, but this is the topic of my last lecture, so which is on Thursday. For today is all. Thank you very much.
Very thought-provoking talk. So in the rate-induced tipping, your rate you have considered as a constant.
It's wait. Yeah. No, I see what you mean, but let me see. Probably it's better to go like this. Let me stand here because it's much faster. Wait, here. So what people usually do is having rates like this. So it can be an arbitrary time dependence. Of course, what you do first is usually something linear. This is the simplest what you can do, which we did here as well. But in principle, it's arbitrary. So all what I said is for arbitrary time dependence. And what people also try to do is, because this is also something which comes in principle from the application. So because most of the parameters you cannot vary from minus infinity to infinity, it doesn't make any sense. So in population dynamics, of course, if you change parameters, there are usually some bounds. So in between, you can change parameters, and this is what you have to respect to get reasonable results. And from a mathematical point of view, people also try to have such a characteristic, either down or up, because when you are here in time, then you are in the usual situation where the parameter is constant. That means you can wait until you are in the attractor, so that you are starting from a definite point in your bifurcation diagram. This is often done. And the same here, because then you are again back to classical nonlinear dynamics theory. So you are again with a status where your parameter is constant, so that the two boundary states are well known, so from classical theory. But what's happening in between is the interesting bit. So because this is then completely different. But in principle, you can also take and this is what we also did already, and many others also, you can just start with climate change and don't go to the attractor. So. This is a very good question. Yes, you can. You can reverse the tipping. So there are only a very few papers on it. So the one who has started this research, coupling rate-induced tipping with noise-induced tipping, is Chris Jones from the US. And they showed already that you can reverse things. But you can also accelerate it. So because it depends on, so to say, who is faster in a way, the noise or the rate-induced tipping. And we are studying this now in ecosystems as well. And it turns out that seemingly, at least for the system we have studied, we see an acceleration of tipping. So when we couple the two. And this would mean we have a higher vulnerability with respect to perturbations. And this is not what we really want, but this is what we have to expect, perhaps. You can have hysteresis, yes. And this has been studied also quite a bit. I will discuss it also tomorrow in my talk. So because we also studied a kind of hysteresis phenomenon, because this is a very important point in climate science. So because we don't know where the threshold is normally. So that means, so people start thinking of when we have crossed the threshold, then of course, so I have shown it. So where is it now? Let me see. Yeah, we have a blackboard. Yeah, this is much better. Much better. When we have such a hysteresis, and I have shown you that it jumps like this. Oh, this is also, so to say, a very special case, because it depends on your speed, how you go here. Because you can jump like this. And you can, when you are here, so to say, when you are starting here, you can go also here, but then go here. So these are all possibilities which are coming up. And then hysteresis becomes important. So people start thinking, since it takes a time, and now it's again a time scale problem, it takes a while to get here. Can we design strategies when we realize, oh, we are over the cliff, so now we have to act fast? So let's try to get back. And so these are things which have been studied by Paul Ritchie, for instance, in Exeter. So they really show under which conditions and how fast you have to react on your perturbation, so to say, when you go through this hysteresis back and forth, how fast you have to be that you are not ending in the other state, but that you can gear the system in a way back to the original state. Yes, so this hysteresis you can do.
The difference in dynamical time scale become our only parameter.
Both. We consider both. So we consider both. Yeah, I forgot. This is a very good question because I forgot to mention this, that we have in principle two timescale separations. So because the timescale separation between predator and prey, and we have the timescale separation to the parameter change. Yes. So there are in principle two timescales important. We have not checked this because for the ecological systems, this timescale separation is inevitable, and it would not make any sense not to have it. So therefore, I cannot make a prediction, but it's not necessary in principle because many other people have studied other problems where this timescale separation is not there, and you see still tipping, rate-induced tipping.
Is it now more or less the general consensus that we are dealing with rate-induced tipping rather than?
No, not at all, I would say, even not at all. Both are possible because in the climate system, so some of the timescales are really such that changes. So for instance, in the Greenland ice sheet, so then the melting is quite a slow process, but so the Atlantic overturning is much, much slower. So so there is also a timescale separation between those. So therefore, there is rate-induced tipping, what people consider. But when you think about changes in precipitation patterns, for instance, or something like that, then rate-induced tipping, I know one paper, I think, where they also looked at vegetation models so that you can have rate-induced tipping, but mainly they still think about, say, bifurcation tipping. Yeah, both are possible. It always depends on your timescales. And this is something which is not discussed in many papers. So what are the timescales they are talking about? So this kind of idea that you have to look at the timescales to see. So should I look for bifurcation tipping? Should I look for rate-induced tipping? So this is often completely neglected.
Maybe I'm wrong, but it's my impression that in the last 5-6 years, the thinking point papers are talking about it in rate, like somehow rate-induced tipping.
Yeah, you see, these are fashions, I would say. So because this is the latest bifurcation which has been discovered, but for ecological systems, I think there is a very good reason for it. Because as I'm in an ecological institute, so and as we discussed already in the break, so I have a big opponent in my institute, and ecologists don't believe in bistability or multistability. So they think the data will not show this. This is all what people have. I would even formulate the claim that so this is cooked up in a way. So the data would not show it, this kind of bistability or multistability. And then rate-induced tipping is the only transition which can happen. So because then this is the only critical transition, at least I know at the moment, so where you don't need two stable states. So this is the only one where you can really go, so to say, from one stable state and you still have a tipping into another state, which depends only on the rate. And this is a candidate for ecological systems. The problem is that in most papers, so which talk about, say, tipping in ecological systems. They never mention the timescales over which some data are collected also. So we have no idea. But this is the only convincing example, so to say, for ecologists, which believe that mostly the ecosystem has one state and there are not others in such a system. And then this is, from my point of view at the moment, the only possibility how we can explain that tipping can occur.
Take a bit of time to digest. Finally, has talks.
Yeah.
Yeah. So